I'm Jimmy Pruitt. I am the team lead. I handle all the management of the team, including setting up the burn down charts and the scrum board and things like that.
I'm Brandon Edwards. I'm the UI lead. I'm in charge of the design of the user interface and how it interacts with programming.
I'm Wesley Kozrowski. I'm testing lead. I'm basically just in charge of making sure that everything works the way it's supposed to.
And I'm Emily Wallen. I am the documentation lead, and I am responsible for everything that needs to be recorded in written English.
Today we're going to be talking about PhytoLab. Our client is Dr. Linhart, who is a CW professor in the math department, and he's also in the audience. And our advisor is Dr. Johnson. In today's presentation, we'll be covering problem statement, Team Python's development approach, project requirement, functional and non-functional.
Paulina, can you please speak up?
Live demonstration, client involvement, and risk management strategies.
PhytoLab is a phytoplankton population modeling application. So a good place to start is, what is phytoplankton? Phytoplankton are photosynthetic microorganisms that are a key component of pretty much any aquatic ecosystem. They're free-floating. They draw their name from the Greek phyto for plant and plankton for wanderer. And they're a very important food source for all kinds of aquatic animals, including whales, fish, and invertebrates. So why is it important to monitor phytoplankton populations? Well, if phytoplankton are allowed to grow out of control, they can cause toxic and very harmful conditions for both wildlife and humans. You might have heard of a phenomenon called red tide, which occurs when a certain red species of phytoplankton is allowed to grow way out of control, and the toxins that they produce start paralyzing local animals and harm the humans that try to eat them. We're starting with a modeling tool that Dr. Linhart already built, and she built it in MATLAB. It has a few basic capabilities. It can solve differential equations that model phytoplankton population behavior, and it can display the results of those differential equations as savable graphs. It has a lot of limitations, though. First of all, it doesn't have a user interface, so it's not friendly to users that aren't familiar with how the application is put together and aren't familiar with code and how to work with it. Another problem with the application is that it is written in MATLAB, which is proprietary, and that means Dr. Linhart has to pay for her subscription to it and monitor it so she can make sure it's been renewed. It also has limited forms of input. Users have to input their data manually, field by field. And finally, the application has no web presence, so you can only use it if it is physically present on your computer, which is not very convenient for our users. And that brings us to the problem that Team Phyto is confronting. We need to convert Dr. Linhart's existing application from MATLAB to scientific Python, and then create a user interface for it. So why are we doing this? Part of the reasons are budgetary. Scientific Python is free and not proprietary, so Dr. Linhart will be able to use it indefinitely without paying for it. It also gives us a great opportunity to add functionality to Dr. Linhart's application. We'll be able to add a bunch of features. Not only will our application solve differential equations and produce graphs from them, like Dr. Linhart's application already does, but it will have a simple and novice-friendly desktop interface, so that people who aren't familiar with code can use it easily. It will also have a web interface so that anyone in the world can use it for free without downloading any unnecessary files. And finally, we'll build an online image database for the project so that people can not only save their graphs to their own desktop, but to a database so that all users can eventually see the graphs.
Team Phyto utilized an agile process development known as Scrum, if you're not familiar with it. Wesley will give you a brief rundown of some of the components we used from it in just a moment, but we felt that it was going to benefit us most because we're all unfamiliar with the project domain and we've actually never experienced Python before either. So we felt like this sort of iterative, good enough prototyping type process would benefit us the best. We could get a prototype, as you will see here, and slowly add on the features as Dr. Linhart gives them to us, and there are actually a few that we haven't implemented yet that we will very shortly. And it also lends itself to short duration projects, and it's a very egalitarian system where everyone is sort of considered equal.
As Julie just mentioned, our team used several different agile processes during the duration of our project so far. One of them is we had tri-weekly stand-up meetings. So our team got together 3 times a week with as many people as we could. And we just went over what had been accomplished so far, difficulties we were facing, and what was expected of us for the next time that we met. We also had weekly meetings with our client, Dr. Linhart, and we meet with her to show her our progress. She let us know kind of what was expected, and she was also an excellent resource to come to when we needed help with some of the more difficult mathematical problems. We also used the planning poker thing that we learned in CS 480. So we had all of our requirements, we listed those out, and we assigned them amounts of time, so we kind of had an idea of how long everything was going to take. We also created a Gantt chart, and it basically scheduled all our work so we could see what we were supposed to be doing, and we'll have to make a greater effort to stick to that the next time around. We also had coding standards, but Python helps us out a lot in that regard, since it's very white space dependent. Sort of thing looks very neat and tidy. We use pair programming, so we all have our individual tasks, testing lead, just lead in general, but we're also able to go and help each other out when we're needed, so not one person is responsible for everything. Also, we have collective code ownership, so not just one person has all the code, we use version control, so everybody is always up to date. All right, so the functional requirements that our project includes it's going to be able to solve a vast number of differential equations and plot graphs for all of those. It's going to be able to plot the substrate concentration for various species as well as various nutrients. It's going to be able to plot the population over time for those species, and it will also be able to plot the optimal resource ratio for the species and the nutrients. It will also be able to accept input from Excel and CSV. The non-functional requirements, in the end, it's going to be able to accept and reject different kinds of input. As the project currently stands with Dr. Linhart, there's no room for error, but when we're finished with it, we'll be able to accept different input, and we'll be able to tell the user what's acceptable, what's not acceptable. We'll be a more user-friendly experience in general. We'll also have a user interface, so more people who are less familiar with mathematics and coding will be able to use it. It will also have a web presence, as was mentioned earlier, so it will be available for more people. And you will also be able to save your graphs online, also locally to use later on.
So in a minute, Brandon is going to give you a demonstration of the prototype that we have so far. There is a lot of math involved. Due to time constraints, we did not actually provide the definition of the math, but it utilizes 2 differential equations in particular that have a series of variables involved. Essentially, scientists utilize what is known as a chemostat setup. This will actually simulate a system that is dependent on phytoplankton. And there's a variable in particular, it's denoted V on the prototype. That is the flushing rate as water flows into the system and also as it leaves on the other side.
All right, and now I'll walk you through a live demonstration of our prototype application. As you can see here, there are several inputs, and these are the variables of the equations that produce the phytoplankton models. The mu max represents the maximum growth rate of a specific species of phytoplankton, and each growth rate is separated by a comma. The Ks represents the half saturation coefficient of the substrate-dependent population growth. The S represents the fixed concentration of the source nutrients, whereas the Q represents the fixed cellular content of S for a specific species of phytoplankton. And then the V is the flush rate of the chemostat, which Jimmy just explained. Now you can enter these values manually, or you can enter them through the use of the CSV file by pressing this button here. And then you can select which models you wish to create. Now I'll demonstrate how our prototype application can reproduce accurately Dr. Linhart's results. So for the first draft, I will upload the data and then grab it.
You have to check it first.
Oh. Right. And then as you can see, the results are the same. And then I will do the same for graphs 3 and 4. You can see it produces the same results. And it is important to note this is a prototype, and there are still variables to introduce and more models to create, but I think it is a strong proof of concept. And that concludes the live demonstration.
So, since Dr. Linhart is so familiar with coding, she's actually in the past had a lot of experience with it. She was very involved in our process, and the GUI, or the user interface in general, was not a high priority of hers. So we only just recently added the prototype, or the GUI to the prototype, and we were not able to get her impressions of it in time. But she did have a strong collaboration with us during the process, and she helped us quite a bit, as Wesley mentioned. So we'll see that in the future, what her impressions are. And finally, risk management. As Wesley mentioned, a lot of the Scrum practices that we utilized, we feel were actually very good at managing risk already. For example, Gantt charts and burn down charts and the Scrum board, those were all ways of assigning tasks or delegating it for people to do, so nobody was working on the same task and everybody knew what everybody else was responsible for. But ultimately, most of those risks involved boil down to communication. As long as we were able to communicate with one another, we felt that risk would be heavily mitigated just by that.
Team Phyto has introduced to you our phytoplankton modeling application prototype and explained our design philosophy, our team composition, and our strategies for risk management. We look forward to adding more graphs and more options to our application and to putting it on the web along with the database for use by anyone. Thank you for listening, and we will take any questions you have.
Can you clarify who is actually programmed solution of differential equations?
Okay, so in the application inputs the differential equations into a differential equation solver, which is part of the matplot libraries, and then those results are then input into another function within the matplot libraries that graph those results.
No, MATLAB was before. My understanding that you want to remove MATLAB.
Oh no, it's a library for Python. It's called matplot.
Okay. So, okay. Then the question is, what is your programming effort is? So if you coding libraries, am I right? Different type of libraries, including the library for the graphical representation. Am I right?
That is correct. Yes. The largest part of this endeavor is actually translating the code into MATLAB, so there isn't a lot in the way of creativity or whatever from MATLAB into Python. But the actual differential equations are of the difficulty that that's what we've been tackling so far.
They've also done all of the work with the graphical user interface, and they've had to learn a substantial amount of math in order to do what they've already done. That's unfamiliar to them because I don't think any of them had a differential equations course.
Yes, thank you.
So what's the status of implementation now? You have shown already implemented in Python?
There are actually a great deal of more graphs, and that is sort of where we're headed in the near future, implement all those before we get